Hi, this is a short video on section 12.1 from our textbook, and it's about inference for linear regression lines. What we're going to do in this video is we're going to check conditions, because anytime that we do inference, we check our conditions. We're going to interpret some values in terms of a population and a sample. And then we're going to construct and interpret confidence intervals and perform a significance test. So very similar to what we've been doing this entire semester, but it's all now about regression. So in regression, remember that we're looking at a scatter plot. So a scatter plot shows a linear relationship between a quantitative explanatory variable x and a quantitative response variable y. So last chapter was all about categorical data. This is about quantitative data, and we're going to be looking at a lot of scatter plots. And we're going to figure out our least squares regression line from the data. And it's either going to be done on our calculator, or what most of the things that we're going to see are going to be done with computer output. And so what we need to kind of recognize is that there's sort of two questions that we're trying to answer with this inference test. The first question is there really a linear relationship between the x and y population, or could that pattern that you see when you make a scatter plot just have happened by chance? And then the second question is, in the population, how much will the predicted values of y change for every increase of one x unit? So kind of looking at that slope. And then what's our margin of error for that estimate? So that's kind of what we're going to be doing in this video. I'm going to be telling you some details. I'll be going through a few examples. But again, remember that much of the work is going to be done for us using our calculator or computer outputs. So here's our first sort of example. It says, below is a scatter plot of the duration and interval of time until the next eruption of Old Faithful happens. And they had 222 recorded eruptions in 1 month. And there's a least squares regression line for that entire month. So they consider this the population for that month. And they consider the population regression line to be the true regression line. And many, many times we don't actually get a true regression line because we don't actually do something, again, for the population. It's kind of like a census. It takes too much time. So instead, suppose you went out to Yellowstone and you only took a simple random sample of 20 eruptions in that 1 month, and you decided to calculate a least squares regression line. And you can see right here that our least squares regression line is y equals a plus bx. We write it a little bit different as statisticians. And the question is, how does the slope of the sample regression line, so when we looked at just 20, how does that compare to the overall population regression line? So when we looked at just 20, how does it compare to those 222? So here's sort of an example, or actually 3 different examples. So the figures below show the results of taking 3 different simple random samples of 20 Old Faithful eruptions in the month. Obviously, they look different because we know that our samples vary. And if you start to analyze them, you should notice that in this example, the slope is 10.2. In the second example, it's 7.7. And the third sample, it is 9.5. So they obviously vary quite a bit from each other, as well as they vary from what those 222 in 1 month were. That they actually had a slope of 10.36. And so as we're looking at that, we want to know, okay, is that something that we should be surprised by, or are these samples just, is that fine? If we just saw a sample of this, would we be able to make any predictions? So again, confidence intervals and significance tests are going to be specifically about the slope. And again, the slope we refer to as B. And if we decided to take, again, and look at the shape of all the slopes, as we can see that the distribution of all the slope values, or B values, is roughly symmetric and unimodal from the picture. If we decided to find the mean, again, it says I took 1,000 samples of size 20, we come up with that the b-value, or the slope average, is 10.35. So the average of all of your samples is very close, or should equal your population average, just as we've seen in previous chapters. And the spread, the standard deviation, for those 1,000 b-values is 1.29. And again, later we'll see how that's calculated, and really it's just done using computer output. So just as we've done before, we always look at the distribution, the shape, the center. Again, there's not outliers, and spread in whatever variable we're trying to study, whatever variable we're doing inference on. Again, this can be found in your textbook, but it just kind of reminds us and summarizes everything that we were just saying in those pictures. So you're always going to be choosing a simple random sample of a certain size, and you're going to be trying to make a least squares regression line. And again, B stands for your slope, and that's an estimate of beta, your slope of the population. The standard deviation of the sampling distribution of B is actually found using this formula, as long as, again, we meet that 10% condition, which is the population is greater than 10 times our sample. Even though they show you this calculation, again, we're going to be doing it on our calculator, or they're going to be providing it as a computer output. So don't worry too much about the equations. And then the sampling distribution we saw was, symmetric, unimodal, and we'll be able to show that it follows an approximate normal distribution. So again, just a summary of that distribution of the variable we're trying to draw inference on. The conditions, there's actually a lot of conditions, and they sound really intense, and we're going to walk through a quick example to show you that they're not as bad as they seem. So again, conditions for regression inference, you have to show that it's linear. And again, the actual linear relationship between x and y, it looks like a line. You basically just look at it and say, it looks like a line. We also will look at something called residuals that we had studied back in chapter 3. In class, we'll talk about how do we find that plot if it's not provided on our calculator. We want to do that independence test again, and that's the 10% condition that we've been checking. We obviously want to look to see if it's normal. And then this newer one is, does it have equal standard deviations? And we'll again show you how you can see that by looking at your residual plots. And then the last one, as we've seen in every single inference that we've done, is the data random? So those are the conditions. Again, what's really nice in your book is they also provide you with how do you check them. And so they provide you with this little list of like, okay, what you really should do is you should make a graph. And they suggest a histogram or a normal probability plot and your residual plot. And all of those can be made on your calculator, and they might even be provided for you from computer output. So again, linear, it just says look at the scatter plot, check to make sure that the overall pattern looks like a line. You should also look at the residual plot and just make sure that it's sort of centered around 0. The residual plot should look very scattered. There shouldn't be any pattern to it. Independent, it's again looking at how was the data produced. So random sampling and random assignment helps to ensure independence. If you, again, were unable to do it with, where it says it's done without replacement, we check that 10% condition. The normal condition, again, that's why we make the histogram. You can make a stem plot. That's not done on your calculator, or a normal probability plot. You're just, again, looking for major skewness, outliers. That's your way of checking normal. We've done that before. This new one is you want to make sure they have equal standard deviation. So again, you look at that residual plot and you look at how are they spread out, and you just want to make sure that they're sort of equally spread out throughout the entire data set. Not that you're, as it says, it should be roughly the same from the smallest x value to the largest x value. So that it's just all about the same distances away, not that one end has higher, is farther spread out. And then the last one, just see how your data were produced. Hopefully it was a random sample or random experiment. So really nice, quick way to, again, nice checklist of ways to check if the conditions are met. Now this is assuming that the problem doesn't say the conditions are met. Many of the problems in this, under this topic, they say the conditions are met. But let's just really quick look at an example. If you turn to page 759 in your textbook and you look at question number 3, question number 3 is about blood alcohol content, and it really just wants you to check the conditions. So if you take a minute, pause, read the video or read the problem, and then we're just going to quickly kind of go through question number 3. And we're going to say, okay, using these two graphs, how can we check those conditions? Okay, so condition 1 was linear. Now, they didn't give us a scatter plot for this problem. They just gave you a residual plot and the histogram. But again, when you look at the residual plot, you should notice that there's no pattern to the residual plot. It's all spread out, scattered, and that's what you want to see to meet that first condition. So you'd have to provide this graph if it's not provided, and then just say, there's no pattern to the residual plot. Independent. As you were reading the problem, you could do it 2 ways. One way is just knowing, like if you knew your friend's blood alcohol content for one subject, that doesn't affect the next person's blood alcohol content. So that's a way of showing or listing or saying that those two values are independent. The normal condition, again, that's why they made the histogram. Again, it's not strongly skewed, it's slightly skewed, but it's not strongly skewed, and there are no outliers, so we met our normal condition. Equal standard deviations, again, you look at the residual plot and you start to say, okay, most of the points, as I keep going, are about the same distance away. Maybe this one's farther away than this one, but in general, they are just scattered about. There's not a pattern or anything strange. All the values seem roughly equal. And then random, it says it was a randomized experiment. They decided how many, it said like each volunteer drank a randomly assigned number. So that would just be how you would check it. You'd list all of those in words. You'd have to provide the graphs if they weren't provided for you. That's just how you check conditions. These next few slides I'm going to go through very quickly because our video is going to end. And then you'll have to pick up in the part 2 video. So again, when your conditions are met, what you're really trying to do is estimate some unknown population parameters about that true regression line, about, again, that whole population that's going on. And there's a lot of words on this page, but it's basically just reminding you that the slope, or the slope of your sample, is what we're going to use to represent or to estimate the slope of our population. The y-intercept of our sample, we refer to it as A, and that's going to help us estimate the y-intercept of our population. And then the standard deviation that we were kind of checking before, we refer to that as sigma, we're going to use an S, as it's describing down here, we're going to use an S to estimate that sigma for the entire population. And so as we kind of wrap up this video, our next video is going to start with an example of how do we estimate those parameters.